Welcome back to the channel. In today's video, we're going to discuss correcting skewed data. Skewed data can impact your data analysis in many ways, some of which you might be less familiar with. But in short, most of the machine learning models you might be building are based on the assumption that the data is somewhat symmetrical. What do I mean? If we have a data set that looks like this, some Gaussian distribution, the mean is here, and roughly the value on both sides of the mean are about 50%. And so when we have skewed data, let's say we have something that looks more like a log normal distribution where we have a long tail on the data set. This can really impact the performance of your model. And so when we talk about correcting skewed data, what we really want to do is compress it. So these larger values out here, we want to shift closer towards the mean. And of course, if we do that, sometimes you will see a shift of the actual mean value. That's okay because those smaller values will shift less. If we have a value, say a value out here that will be 16, and we have a value near the mean, let's say the value is 2. The distance between that is just the distance, 16 minus 2, and that equals 14. That would be the uncorrected data. Now let's say we apply a square root corrector to the data, and so we take the square root of 16 minus the square root of 2, and that now would represent our square root corrected data. So now we have 4 minus 1.4, and that approximately equals 2.6. And so now we've gone from having a value of close to 14 units apart, to now only 2.6. Thus, these values out here will move much more than these values here. And that's really what we're doing when we talk about scaling the data. We could extend this to taking the cube root or the fourth root or log distribution, or apply the log of these values. And that's what we're going to do in our notebook right now. And so here we have a notebook with a few modules that we're importing: pandas, NumPy, matplotlib, it's seaborn for plotting, as well as scipy.stats. We'll talk about this Yeo-Johnson corrector here in a little bit. So in the next cell, we will create two distributions, one which is a log normal distribution with 1,000 samples, and then the other is a Gaussian distribution to kind of anchor us and understand what that normal distribution looks like. We're going to set the random seed to 3 so that each time we run this, we get the same output. So if you want to do this on your own, just set your seed to 3 and you will get the exact same output I get from this data set. As well, we're going to calculate the skewness of the data set, this asymmetry of the data set, as we apply these correctors, just so you have a sense of how it's moving and do that in a quantitative manner. So if we run the cell, you see I've already calculated the skewness of our normal distribution. This skewness is close to 0, and our log normal distribution has a skew of about 7.2. By many factors, we're really hoping to get the skew to be between negative 0.5 and positive 0.5. That's considered to be symmetric enough. And so the closer to that range we can get, generally the better. And there might be certain trade-offs depending on the models, but that's beyond the scope of what we'll discuss today. In the next cell, we're plotting the kernel density plot of these. This is basically a smooth histogram, and we can see that the blue trace is Gaussian, is very symmetric, and the orange trace is that log normal distribution with this long tail trailing out near 40. And so our hope is now to move that in and sort of compress it so that the high values are closer to the mean and we can reduce the skewness of the data. So let's begin. Instead of writing everything out, I'm just going to copy this and paste that there. And the first skew corrector I want to show is taking the square root. So if we just apply square root using NumPy and plot that data, again, that skewed data is shown in orange, and we can tell based on this x-axis that we have reduced a lot of the skew. Instead of those large values near 40, those values are now compressed down between around 0 to 6. And so you can see how those larger values move more than the smaller values. Let's look at the skew of that piece there. So we just copy that part and use the skew method. You can see that now, instead of having a skew value near 7.2, our skew is 1.9, and we're going to save that into our dictionary. So we'll just call it skewdict. And we'll just call this square root. And we'll create a bar plot at the end looking at that data. The next correction we want to apply is, let's take the cube root of this. So if the square root does some compression, we might expect the cube root to do even more. And there isn't a direct method we can use. However, we can raise this to the power 1/3, which mathematically will give us a cube root. And we can look at this and see now we've even further compressed this data, and it's looking significantly more Gaussian than even the square root. And if we continue this and look at the skew, notably, let me show you what the output is. The output is a Panda series. And so that's how we're able to use the skew method. We just have to make sure we wrap the entire statement in parentheses, and then we can run .skew. You can see now our skew has been further improved to be 1.1. Next, one more in this series. Let's look at the fourth root of this data set. So we'll just raise this to the power 1/4. And you see, again, we compress it even further. We'll repeat this analysis. You see, we've gotten our skewness down to less than 1. And so we can continue to explore this. And these are some of the parameters you might just hope to optimize as you evaluate your models. And we'll save this. Okay. Now, I mentioned in an earlier video, since we know we have a log normal distribution, which tends to be the case for a lot of measurement data, where most of your values are small and you have a few that might have large values, one of the best ways to correct a log normally distributed array is to take the log of that. And so let's look at what that does now that we have a better sense of what skew correction looks like. If we erase this and now just apply the np.log method to that, now we have corrected our log normal distribution to have a mean of 0 and looks very similar to our Gaussian reference in blue. If we copy this and look at the skew of this, we have a very small skew near 0. And so this is ideally what we're hoping to achieve by applying some of these other compressions. But because we understand the distribution is log normal, we would expect this to be the best of the methods we've tried so far. And so let's record this. Next, we're going to look at one more skew corrector. This is called a power transformer, and the math is a little bit more sophisticated than these others, but I still want you to see that, because if you have data that's severely skewed or has some other abnormality in the symmetry, this could be a good approach. That is where this Yeo-Johnson approach comes in. This is out of the scipy.stats module. There's lots of other correctors there, so I advise you to go just take a look and be familiar with it, and we'll use that at the bottom here. And so all we need to do is pass this method in. If I shift tab, just so you can see the equation, you see we have a number of parameters. And the most important here is this lambda corrector. And if you don't put a lambda argument in, this method will actually optimize for the proper lambda. And we can see what that is once we run this method. And so for x, we will just pass in our data set, which is L norm. And we receive this tuple where the first is our array. So this is that data we've been looking at, a NumPy array. And the second value at the bottom here is that lambda value. I'm actually going to copy that. And this is the optimal parameter. And when I put that back in here, this will just help to keep the data in this 1D array. Now we're telling what lambda we wanted to compute based off of. And we can look at the skew. Now this data is an NumPy array, so I can't just use the skew method like I did before, or if I run skew here, we have this attribute error because we're talking about an NumPy array. So the way around that is to use the skew method from scipy.stats. I know this seems kind of confusing in the namespace, but I actually imported skew at the top of the notebook for this particular reason. So now we have another skew value that's between our 0.5 and -0.5 cutoff. And this could be a suitable approach for your machine learning algorithm. There's another similar transformer called boxcox, which if your values are all positive, you can use that. Yeo-Johnson is a more flexible that allows you to input negative values as well, which I know this dataset has. Next, let's plot this last data and see what it looks like. Okay, now you can see that with this particular power transformer, the data is severely compressed. Our range looks like it's now between just below 0 and around 1.5, 1.6. And for most machine learning models, this will significantly improve the performance. And so depending on how your data is skewed, this is a really powerful technique. However, which technique is ideal really depends on the scenario. And I recommend just trying these out, seeing the performance before making a final call. I have this dictionary called Skewed that I want to convert to a series. And next, we're going to plot it so we can see how each of these methods we use to correct the skewness of the data performed. And we can see that our log and Yeo-Johnson are the closest to the normal distribution. And as we continue to increase the power, this looks much better. And so there are many ways to correct the skewness of your data, and it really comes down to what you want to do with it next. Sometimes these really powerful transformers are good. Sometimes it could also make the story a little bit more difficult to understand. And so depending on context, I advise you to try them all. In any case, if you enjoyed this video, like, share, subscribe, and I'll see you in the next one. Peace.